There is a limit to power in our universe, a quiet ceiling woven into the fabric of spacetime itself. Even the darkest giants we know, black holes, cannot cross it. Their gravity can swallow stars. Their hunger can bend light. And yet, there exists a silent maximum to the energy they can hold, a boundary nothing in the cosmos dares to exceed. Tonight, we drift into that invisible frontier, the speed at which information can move, the rhythm of rotation at the edge of gravity, the ultimate tether that binds energy to the shape of spacetime, all whispering the same cosmic truth: there is always a limit. Before we begin, if you're kind enough, a gentle like or a soft tap on subscribe helps these quiet journeys continue. It means more than you know, and I'm deeply grateful you're here. Now, let us drift into the first truth. Part 1. The silent speed limit of the universe. There is a maximum pace for everything that moves, everything that changes, everything that exists. The speed of light is not simply fast, it is the boundary that reality itself refuses to cross. Even black holes with their immense gravity cannot break this rule. Their influence reaches out, but never outruns the light that defines the speed of causality. This limit, about 299,792 kilometers per second, is one of the most profound truths in physics. It is not a guideline or a flexible threshold. It is woven into the mathematics of spacetime itself. Light does not travel at this speed, because that is simply how fast photons prefer to move. Light travels at this speed because this is the speed that spacetime allows any information to travel. In the calm darkness of the cosmos, this rule keeps order. It ensures that cause always comes before effect, that distant stars cannot influence us until their photons arrive, that nothing can jump ahead of its own shadow in time. It is a soft but unbreakable governance over motion. If you could watch a beam of light travel through the void, you would see not just a rapid movement, but the fastest possible whisper of existence. Faster motions are not forbidden by power or technology. They are forbidden by the very geometry of the universe. Even you, sitting perfectly still, are shaped by this limit. Every electrical signal in your brain, every photon reflected from your skin, every atom bound to the next, these are constrained by the speed at which interactions may propagate. Even stillness is defined by how quickly change refuses to arrive. Einstein's theory of special relativity gave us a new way to think about movement. It showed that as an object approaches the speed of light, its energy grows without bound. To keep accelerating requires more and more input until the required energy becomes infinite, and infinity does not exist in the physical world, which means there is always a speed you cannot reach. Imagine a spacecraft accelerating in total silence. The engines flare, the stars drift behind you, and your velocity climbs closer to the cosmic maximum. But each moment of acceleration becomes harder than the last, not because the engines fail, but because spacetime itself pushes back. Mass increases, time stretches. The traveler's heartbeat slows relative to those left behind. Distance itself reshapes, like a fabric tightening around the speeding ship. Approach the limit, and time for you nearly freezes. Cross it, and physics would be forced to do something impossible: let causes occur after their effects. So the universe does not allow it. Even massless particles like photons do not exceed this limit. They simply exist at it. They are spacetime's swiftest messengers, always dancing on the razor-edge boundary of what can be known. And what of black holes? These are the most extreme objects we know, where gravity becomes so strong that even light cannot escape. When a black hole forms, it creates an event horizon, the surface where escape becomes impossible. But even here, the speed limit quietly governs behavior. Light inside the horizon does not slow down or weaken. It simply finds that every possible path now leads inward. The structure of spacetime bends so sharply that moving forward in time is the same as falling deeper into darkness. Nothing escapes the horizon, because doing so would require faster than light motion, and the universe refuses. This limit also shapes how gravity works across distance. Though we often imagine gravitational pull as an immediate force, like the Earth tugging on the moon without delay, modern physics shows that gravitational influence moves at the speed of light as well. If the sun suddenly vanished, Earth would not immediately fly into the void. It would continue orbiting for a little over 8 minutes, the same delay as sunlight. Before spacetime updated the news, even gravity must wait its turn. This constancy reveals a quiet beauty. The entire cosmos moves together, under one rule. No star rushes ahead of time. No galaxy receives the whisper of a distant collision before light arrives. Every signal, every change, is bound to the same cosmic metronome. If you look out into the universe, the most distant galaxies appear to speed away faster than light. But this doesn't break the rule. They aren't flying through space at that speed. Space itself is expanding beneath them. The speed limit applies to things moving within spacetime, not to spacetime stretching like fabric in the night. The rule has subtlety but never breaks. In quantum physics, this limit takes on an even deeper meaning. Entanglement, a strange connection where particles mirror each other instantly, might seem to violate it. Yet no usable information travels faster than light. Reality protects causality with quiet insistence. Even the strangest phenomena respect the boundary. This limit ensures that your memories remain in the past, that a star's collapse, billions of light years away, will only touch your sky tonight, that the universe, with all its vastness and uncertainty, reveals itself gently, moment by moment, never all at once. In the silence of space, speed is not just motion, it is order. A quiet agreement among all particles and fields that everything must unfold in sequence. So, as you listen now, in this moment perfectly your own, the photons from the room around you race through your eyes at the only speed they are allowed. Stars beyond the sky release ancient light that will arrive here one day, but not until the universe permits it. Time itself is structured by this limit. It is the steady heartbeat beneath every second. Even black holes bow to this law. No matter how massive, no matter how violent their collapse, they cannot pull a signal outward faster than light. They cannot reach into the future. They cannot break free from the quiet boundary that guards reality. As you rest, consider this gentle truth. The universe is not in a hurry. It does not rush. It does not skip its own rules. It unfolds at a pace that protects meaning, sequence, and the calm flow of time. And yet, in that stillness, everything is moving. Light traveling, worlds orbiting, galaxies drifting apart, all of it synchronized by a silent speed limit that ensures we remain grounded in the present just long enough to experience it. And as we continue this journey deeper into the dark and beautiful mechanics of existence, one question quietly rises. If nothing can exceed this ultimate speed, what happens when energy grows so intense that it begins bending space-time itself? Now, we drift into Part 2. Part 2. When energy becomes gravity, in the universe, energy and mass are the same currency. The more energy you confine into a region, the more space-time bends around it. Push too far, concentrate too much, and energy collapses into a black hole. Even limitless ambition meets a gravitational wall. This idea comes from Einstein's most famous equation, E mc2, a quiet statement that energy is mass and mass is energy. They are simply different forms of the same essence. Wherever energy gathers, gravity deepens. Wherever mass moves, it carries energy with it. These two concepts, once thought separate, are bound tightly by the structure of space-time. Gravity, then, is not a force that pulls from afar, but the shape that energy creates within the universe. Everything that exists bends the fabric of reality around it. Even the smallest particle leaves behind a curve. Even a beam of starlight has weight in the geometry of existence. The more energy you add, the sharper the bend becomes. Imagine a plain sheet stretched flat, space-time when empty. Now, place a single marble on it. The surface dips slightly, gently. But if you drop a bowling ball in the same place, the dip becomes deeper, drawing other objects inward. Now, imagine a star, a roaring furnace of fusion, bending the cosmic sheet so strongly that planets fall into steady orbits around it. Here, gravity is not an invisible hook, It is motion following the natural slope of spacetime, but energy is never content to remain peaceful. As a star burns through its fuel, the delicate balance of pressure and gravity begins to shift. Under enormous weight, atoms are crushed, energy becomes trapped, and when the star's core can no longer resist the pull inward, a collapse begins, fast, silent, unstoppable. What was once radiant becomes dark. What was once structure becomes pure gravity. A black hole is born, a region where energy has curved spacetime so sharply that the slope becomes a pit with no floor. Inside, the future only points downward, deeper into collapse. Outside, the surface of no return forms, the event horizon. It is not a barrier made of matter, but a threshold drawn by geometry. Cross it, and every path leads inward. This transformation from light to gravity happens not through destruction, but through concentration. Energy has become too dense to remain free. Mass has folded under its own weight, and the universe, following its own rules, allows no escape. The amount of bending required to form a black hole is astonishing. A mass like the sun must collapse into a sphere only a few kilometers across. A mountain's worth of mass squeezed into something smaller than a single grain of sand. And if you tried to compress even light with enough energy into a tiny region, it too would collapse. Brightness becoming darkness, motion becoming stillness, information becoming hidden. But this is not chaos. This is the universe enforcing boundaries. Gravity rises from energy, and energy has limits. When physicists study the universe's earliest moments, they discover the same principle at work. After the Big Bang, all of existence was dense, unimaginably so. Space itself was curved into extreme shapes, rippling with energy. It was a time when gravity and quantum chaos were indistinguishable, woven into a single turbulent state. As the cosmos expanded, energy spread out like ink diffusing through water. The curvature relaxed, gravity softened, stars formed, not from infinite density, but from clouds with room to breathe. In this gentle separation, structure emerged, galaxies spinning, stars igniting, planets cooling, life beginning. Gravity is not an obstacle. It is a sculptor. It arranges matter, holds orbits steady, protects atmospheres, shapes worlds. Without gravity's patient pull, the universe would be an endless fog of hydrogen drifting forever, too still to ignite into anything meaningful. Yet, even the sculptor must be tamed. If gravity grows too strong, if energy crowds too tightly, the creative force becomes a consuming one. The same law that forms stars can erase them. It is a balance that defines everything, from the orbit of Earth to the breath you take. The universe cannot allow infinite compression. Even at the heart of a black hole, the singularity we imagine, infinite density, infinite curvature, is likely a reflection of our incomplete understanding. Space and time resist infinite values. At the smallest scales, quantum physics hints that spacetime itself becomes granular, resisting further collapse. There's a limit to how much energy can fit within the tiniest region. Beyond that limit, gravity and quantum rules must rewrite themselves. This boundary is called the Planck scale, where gravity becomes not a smooth field, but a storm of flickering geometry, where space trembles with uncertainty, where energy can no longer be confined without creating instability. Across all extremes, the same truth emerges. Energy can shape reality, but never fracture it. Even black holes, monuments to collapse, are stable only because the universe refuses to let them exceed what spacetime can contain. They do not grow into infinite monsters. They radiate, they evaporate, they follow rules as old as the cosmos itself. If energy wants to deepen gravity, it may. But if it tries to exceed natural boundaries, the universe pushes back. This restraint preserves causality, it protects time from unraveling, it keeps the future from folding into the past. And as you rest here, listening, every movement of energy in your body, every electrical spark in your nerves, gently bends the spacetime beneath you. It is so slight you never notice, but it is there, a quiet conversation between your existence and the universe that holds you. Gravity is a reminder that you are not separate from the cosmos. You are part of its geometry, a contour in its shape, a participant in its symmetry. In every star that collapses, in every galaxy that clings together by invisible threads, in every black hole hiding a secret core, energy becomes gravity. Not as punishment, not as constraint, but as balance. And as we continue deeper into this quiet, enormous topic, one question gently rises from the silence. If gravity is what energy creates when confined, what happens when spinning energy pushes back against collapse? Now we drift into part 3. Part 3, the black hole that spins too fast. Black holes rotate. Some whirl so rapidly they approach a theoretical barrier, the Kerr limit. Spin beyond that, and physics insists the black hole must expose a naked singularity, a place where the laws of nature cannot hide their secrets. But the universe has never allowed such a thing. Rotation is not a detail. It is a fundamental behavior written into almost every object in existence. Stars spin, planets twirl, galaxies rotate in vast spirals of dust and light, and when a massive star collapses into a black hole, its angular momentum does not disappear. Instead, it intensifies, the way an ice skater spins faster when pulling in their arms. The collapsing star becomes a vortex in space-time itself, a rotating black hole. Physicists call these spinning giants Kerr black holes, named after Roy Kerr, who first described them in 1963. They are some of the most extreme objects in the cosmos. Around them, space-time does not simply curve inward. It twists, it swirls, it drags everything with it in a silent tornado of gravity. Near a rotating black hole, nothing can remain still. Even light cannot resist the pull of rotation. A region forms outside the event horizon called the ergosphere, where space-time is swept around so violently that every object must spin in the direction of the black hole's rotation. Here, the quiet rules of motion are replaced by a cosmic current. Particles cannot choose their direction. Space-time chooses for them. But there is a limit to how fast space-time can twist. At the heart of every Kerr black hole lies a singularity, a point where density and curvature become extreme. In a rotating black hole, this singularity stretches into a ring, a perfect circle of infinite compression. The faster the black hole spins, the more this ring flattens, pulling the event horizon inward, making the veil of darkness thinner and more fragile. If the spin reached perfection, a dimensionless spin of exactly 1 in the units physicists use, something dramatic would occur. The event horizon would vanish. The singularity would be laid bare to the universe. Cause and effect could break down. Time might lose its direction. Physics, as we understand it, would no longer be able to protect its secrets. This is called the Kerr limit, a cosmic speed limit for rotation. Yet nature has never shown us a black hole that crosses it. Even the fastest black holes measured, some spinning hundreds of times per second, still fall short of the theoretical maximum. Observatories like NASA's Chandra X-ray Observatory and ESA's XMM Newton have revealed black holes spinning at breathtaking speeds, but always just a fraction below the Kerr limit. Why? Because the universe is cautious with its extremes. There are several quiet mechanisms working against excessive spin. For one, anything falling into a black hole rarely arrives perfectly aligned with its rotation. Random motion tugs against perfection, acting like a brake. Accretion disks, swirling rings of gas and dust, help feed black holes, but the turbulence inside them prevents flawless synchronization. And as the spin approaches the limit, the black hole resists further acceleration. It becomes increasingly efficient at flinging away the very energy that tries to push it faster. The more you try to spin a black hole, the more it pushes back. This is balance at the heart of destruction. The universe seems to enforce a cosmic censorship, a principle that prevents the naked singularity from ever being exposed. It is as if the mathematics allows the possibility, but reality steps in to ensure stability. Without censorship, the singularity could throw causality into chaos. Particles might travel backward through time. Effects could arrive before causes. Even the geometry of reality could unravel. And so, Every known black hole remains dressed, hidden behind the curtain of its horizon. Spacetime protects its deepest mysteries, but those mysteries still leave traces. The rotation of black holes shapes the universe around them in extraordinary ways. It can launch jets of radiation stretching thousands of light years into intergalactic darkness, beams so powerful they outshine entire galaxies. These jets likely draw their strength from the black hole's spin, tapping into rotational energy through magnetic fields tangled at the edge of the horizon. Rotation also stabilizes surrounding matter. It allows accretion disks to heat and glow, revealing the black hole's presence through X-ray flares. It influences how stars orbit in galactic centers, and if two spinning black holes merge, their combined dance generates ripples through spacetime, gravitational waves, like a deep, silent bell ringing across the cosmos. In 2015, humanity heard this bell for the first time. The LIGO Observatory detected gravitational waves from two merging black holes over 1 billion light-years away. Their spins reshaped the signals, encoding information about how the fabric around them twisted and churned. It was the first direct confirmation that Einstein's predictions, even about these extreme objects, hold true. All of this motion, all of this energy, remains within the boundary the universe sets. No spin too fast, no horizon torn open, no singularity revealed. Even in their intensity, black holes obey a quiet restraint. When they grow too ambitious, the universe steps in with subtle corrections: radiation, turbulence, dissipation, keeping the rotation forever under control. As you breathe here, wrapped in stillness, somewhere out in the night a black hole is spinning thousands of times faster than a kitchen blender. Its gravity warping time, its rotation dragging the stars around it, yet even that wild power is tethered gently by cosmic law. Everything in the universe dances to the same physics: no step too large, no turn too sharp, no spin beyond the limits set by spacetime itself. Black holes are powerful not because they break the rules, but because they push them as far as they can go. And as we move onward in this journey, deeper into the shadows cast by gravity, a new question rises like a soft ripple through the dark. If rotation can never destroy the horizon, then what protects it when charge becomes too strong? Now we drift into Part 4. Part 4. The horizon. That refuses to tear the event horizon is more than a dark boundary. It is a shield preventing information from escaping what lies beneath. If a black hole could exceed its rotation limit, this shield would tear open. Instead, spacetime steps in, restoring order, preserving its quiet secrecy. This horizon is one of the most mysterious surfaces in the universe. It is not made of matter. It has no physical thickness. It is not a wall in any conventional sense. Instead, it is defined by a simple rule. Once you cross it, every path forward leads deeper into the black hole. Time and distance become the same direction. Out and forward no longer have separate meanings. To approach the horizon is to see the shape of time change gently beneath you. If you hovered just outside a black hole, riding on some impossible platform kept from falling, you could shine a flashlight upward, and the beam would struggle to climb away. The closer you get to the horizon, the harder the light must work. At the very edge, the beam would stand perfectly still, frozen in place. Cross that boundary, and light can no longer escape at all. This is the event horizon, the place where escape would require faster-than-light motion, and nothing in the universe is allowed that speed. The horizon is a promise written into spacetime. It says, everything that happens inside remains inside. The black hole may distort time, itself may warp distance into impossible shapes, but the horizon holds firm. What lies beyond cannot affect the cosmos unless the cosmos chooses to reveal it. And yet, this promise is fragile. It must be protected carefully, especially when a black hole spins near the edge of its allowable limit. Rotation twists spacetime, tugging the horizon into an oblate shape, wider around the middle, compressed near the poles. The faster the spin, the thinner this cloak becomes. Push further, and something dangerous lurks. The horizon might vanish. A naked singularity would emerge, a place where infinity sits exposed, where physics loses its rules, and where the universe cannot guarantee order or causality. This would be a breach in the fundamental laws that protect reality from contradictions. But the cosmos does not permit that. Instead, it enforces balance. If a black hole spins too rapidly, it sheds angular momentum. It flings energy outward, it radiates, it adjusts, it keeps the horizon intact. Spacetime itself takes charge, ensuring that secrecy remains. Physicists call this principle cosmic censorship, the idea that singularities must always remain hidden from the outside universe, wrapped behind horizons where their strange mathematics cannot disturb what lies beyond. It is not a written law, but an observed balance. Every black hole ever measured obeys its quiet command. Look deeper still. The event horizon is not only a boundary, it is a memory. A surface where information is stored, encoded in microscopic patterns that we cannot yet decode. Stephen Hawking taught us that black holes are not perfectly black. They slowly evaporate through a gentle glow known as Hawking radiation. And if they evaporate, then information must escape with them, but never before its time. The horizon is not hiding destruction, it is hiding transformation. Every particle that falls inward leaves a tiny imprint on the horizon, like ripples on still water. The surface changes with every interaction, no matter how small. These imprints are subtle, delicate, and scattered across an area that grows as the black hole absorbs more mass. The horizon expands to store more information, never shrinking except in the slow and predictable process of evaporation. In this way, the horizon behaves more like a cosmic ledger than a barrier, recording everything that enters, keeping the ledger encrypted until the universe can read it again far in the future. No secret is lost, just deeply hidden. Even the shape of the horizon follows this logic. Around a spinning black hole, it becomes surrounded by the ergosphere, where energy can be extracted, but only from rotational motion. The core remains protected. The deepest truths stay out of reach. The horizon responds to the cosmic environment, but never loses its role as the guardian of causality. Now imagine this horizon closely. If you were to fall toward it, your experience would be strangely peaceful. Gravity would feel weaker than expected until the last moment. You might pass through without even noticing, drifting inward while the outside universe watches your approach, slow to an eternal crawl. From afar, you never quite arrive. You fade, becoming a whisper on the edge of time. The horizon absorbs your presence gently, stretching your final signal thin across its surface. To the observer outside, the horizon always wins. It never breaks, it never tears, it absorbs change and remains whole. Inside, the singularity waits, but no glimpse of it ever escapes. This quiet perfection holds the universe together. Without the horizon, the singularity could influence distant events with no mediation, no rules. Physics could be rewritten moment to moment by truths too intense for structure to survive. Instead, the horizon softens the collapse, cloaking the extremes beneath its smooth geometry. And like all laws enforced by the cosmos, this protection works through limits. The Keir limit prevents over-rotation. Charge limits prevent over-repulsion. Even the total amount of information a horizon can store is tied to its surface area, a limit that connects gravity to entropy in ways we still seek to understand. Every extreme in the universe is met with gentle restraint. Black holes are not monsters tearing spacetime apart. They are custodians of its integrity, reshaping matter and energy, but always within boundaries. Even at their most violent, they maintain harmony. Even at their darkest, they follow laws older than stars. Tonight, somewhere far away, a black hole is devouring a star, tearing it apart into streams of plasma, and yet the horizon stays calm. Nothing escapes, nothing leaks, nothing breaches the secrecy. The singularity remains protected behind a surface that has no substance but absolute authority. The horizon may represent the edge of what we can know, but it is also the reason we can trust the universe to remain consistent. As you breathe gently, here, grounded and safe in your place within space, This cosmic law, the preservation of horizons, keeps reality coherent. It ensures that even the most powerful objects follow rules. It reminds us that the universe is not chaos, but ordered mystery. Even darkness has boundaries. And as our journey continues, another question quietly emerges from that boundary. If rotation and gravity cannot tear this horizon, what happens when electricity adds its pull? When a black hole tries to charge itself beyond what spacetime allows? Now we drift into Part 5. Part 5. The maximum charge. A black hole can hold electric charge like spin has a limit within a black hole. Past that point, electromagnetic repulsion becomes too strong. Rather than collapsing inward, the structure would destabilize. But nature intervenes, forbidding the charge from ever reaching that threshold. A black hole is more than a well of gravity. It can possess mass, rotation, and electric charge. The three quiet qualities that fully describe it in the language of general relativity. Charge gives a black hole a new kind of influence, not just the pull of spacetime, but the push and pull of electrical force. Matter falling inward does not simply disappear. Its charge remains, recorded in the black hole's fundamental character. Physicists call these electrically charged black holes Reissner-Nordstrom black holes, elegant in theory, rare in nature. For a black hole to build charge, matter must fall in unevenly, favoring one charge over the other, more electrons than protons or more protons than electrons. But the universe resists such imbalance. Charges attract their opposites fiercely. Every excess attracts its own correction. Still, imagine it happening. A black hole gaining charge bit by bit as negatively charged matter falls inward faster than positive charge can arrive to cancel it. Electric fields intensify. Photons ripple. The horizon becomes more than a point of no return. It becomes the border of a charged world. Yet every increase comes at a cost. As charge grows, something subtle shifts. Gravity still pulls inward, but the electromagnetic field begins to push outward. It resists compression. It resists collapse. The two forces begin a quiet argument at the threshold of the horizon. If charge reaches a certain maximum, a perfectly balanced ratio between charge and mass, the horizon itself would shrink. Any more than that, and the horizon disappears entirely. The singularity becomes exposed. A naked singularity emerges, breaking the cosmic censorship that protects the universe's order. This maximum ratio is known as the extremal limit. At the extremal limit, gravity and charge reach perfect symmetry. The surface of the horizon becomes thin, elegant. Time near the boundary changes its flow. Space stretches outward into an infinitely long throat. The black hole's temperature falls to absolute zero. Any attempt to push past this balance, even slightly, would create instability so deep that spacetime itself intervenes. No violation is permitted. Nature enforces moderation. Why is charge so dangerous? Because unlike spin, which simply twists spacetime, charge brings a force that can overpower gravity itself. Charge repels charge, like pushes like. Too much of the same kind inside a shrinking volume becomes violent. Gravity says, fall. Electromagnetism says, disperse. Push them both to maximum strength, and only one can win. Yet instead of allowing this conflict to reach extremes, the universe creates safeguards, subtle, natural breaks that counterbalance charge long before the horizon tears. One safeguard is attraction. Opposite charge rushes inward, neutralizing excess. It is nearly impossible to build a large imbalance when every stray particle is drawn to correct it. Another safeguard is radiation. If charge rises too rapidly, the black hole emits powerful electromagnetic bursts, shedding charge faster than it can accumulate. It ejects energy like a pressure valve. Plasma jets and particle streams leak away from the vicinity of the horizon, restoring equilibrium. Even the vacuum of space responds. Strong electric fields can tear pairs of particles out of nothing. Electrons and positrons born from pure energy, and each pair helps reduce excess charge. Opposite charges fall inward to balance the whole, while like charges escape outward into the night. The universe cares about balance so deeply that it creates matter from emptiness to achieve it. And if the black hole reaches the brink of maximum charge, one final truth emerges. Gravity refuses to surrender. A charged black hole still falls inward, still deepens, still shapes space into a pit too dark for return. But it does so gently, remembering that perfect charge would tear its cloak apart. The closer it gets to the extremal limit, the more stubborn its resistance. Just as the black hole approaches full charge, the charge itself becomes harder to add. A diminishing return that protects the horizon. Even energy follows rules here. Even collapse obeys conservation. You might imagine this extremal black hole as a quiet, perfect thing. A frozen geometry, time slowed to stillness. Its surface gleaming with potential energy. Its temperature near zero. It is the most stable object in physics. Yet it stands on the edge of danger. To exceed the charge limit would be to violate causality, to let past and future intermingle, to create a place where information escapes naked from the core, a region without a horizon, a window into the raw heart of physics where equations break and predictions fail. The cosmos will not allow such a view. There is a deeper poetry here. Even the most consuming darkness has boundaries. Even the most powerful collapse has humility. Even black holes cannot become too extreme. Charge limits reinforce the harmony of the universe. Energy and structure remain intertwined. Nothing grows. Without balance, nothing collapses without resistance. The horizon remains whole. Every secret remains contained. Every rule remains intact. As you rest tonight, the atoms in your body are held together by electric charge, a dance of attraction and repulsion that keeps you solid, grounded, safe. If charge had no limit, you could not exist. Matter would tear itself apart. Stars would explode in perfect symmetry. The universe would have no form. Limits are not constraints. They are the reason there is a world at all. And black holes, seemingly pure chaos, honor these limits most of all. They show us that even destruction has laws, even collapse has edges, even the deepest shadows obey guidance. In every quiet corner of space, charge seeks balance, and the universe ensures it is found. As we drift deeper into this journey, a new curiosity begins to form from the calm of these boundaries. If charge and spin both approach perfect limits, restrained by the horizon, then what fundamental principle unites these ceilings? What single truth decides how much energy matter can truly hold? Now, we gently turn the page and drift into Part 6. Part 6. How spacetime protects its own rules. At every scale, the universe enforces boundaries. These aren't punishments, they are the geometric necessities of spacetime. They keep cause before effect. They keep structure from dissolving. They keep reality intact. We tend to think of laws as decisions, rules chosen and imposed. But the laws of physics are not decrees handed down from a distant authority. They are the shape of the universe itself. They are geometry, curves, symmetries, and limits that arise from the way spacetime is built. Imagine a vast fabric stretching in every direction. Every particle, every beam of light, every moment in time is a thread woven into that fabric. You cannot pull on one strand without the others moving in response. That movement, that interdependence, is physics. Spacetime protects itself not by intervention, but simply by being what it is. When a black hole spins near the Kerr limit, spacetime refuses to let it cross the threshold into chaos. When charge builds beyond what gravity can contain, spacetime creates particles from the vacuum itself to restore balance. When energy tries to accelerate something faster than light, the geometry of the universe stretches time and mass to keep the motion within bounds. Every limit we encounter in physics is a quiet safeguard, ensuring the story of the cosmos unfolds in a sequence that makes sense. Cause must come before effect. Space must remain continuous. Time must keep its direction. These are not restrictions. They are the conditions under which existence remains possible. Consider the speed of light limit, not an arbitrary barrier, but the maximum pace at which information can move. If something exceeded it, The consequence would not merely be a faster journey, time itself would unravel. Events could loop. Consequences could arrive before their causes. The fabric of reality would tear, not physically, but logically. Space-time prevents that. Or consider the Planck scale, the smallest distance that retains meaning. Our mathematics predicts that below this scale, space-time becomes a frothing quantum uncertainty, flickering with spontaneous curvature. But the universe never forces us into those impossible depths. It keeps that domain sealed behind the horizon of black holes, away from direct observation. It reminds us that some knowledge must remain encoded until a deeper understanding exists. The same principle holds true with mass and energy. Add too much into a small region, and space-time curves inward to form a black hole, containing what would otherwise become infinite. It prevents energy from collapsing into a paradox. Space-time does not fear extremes. It simply refuses impossibilities. Even something as simple as the conservation of momentum arises from geometry, from the fact that space-time looks the same in every direction. Uniformity gives rise to stability. Symmetry gives rise to order. What seems like a law is really a reflection of the cosmos's own structure. On planetary scales, these rules stabilize orbits. Gravity ensures motion follows predictable curves. Even when stars collide or galaxies interact, the overall balance remains intact. Angular momentum is shared, not destroyed. Energy transfers but never vanishes. Motion may transform, but it never escapes the framework. On quantum scales, boundaries become even more delicate. Uncertainty prevents particles from settling into impossible precision. A particle cannot have both a perfect position and a perfect momentum. Space-time keeps a minimum amount of unpredictability to avoid infinite densities. In this uncertainty lies stability. In this randomness lies protection. Without quantum uncertainty, electrons would collapse into atomic nuclei. Atoms would implode. Chemistry would fail. Life would never emerge. The softness in the universe's laws, the refusal of absolute precision, ensures complexity can exist. Space-time is not rigid, it is resilient. It bends gently around planets. It stretches with cosmic expansion. It ripples when massive objects merge. Gravitational waves, first detected in 2015, are proof that space-time responds to disruption by adjusting gracefully, allowing motion to pass through without breaking the structure. Even black holes, the most extreme manifestation of collapsed space-time, are caretakers of order. Their horizons ensure that the singularity remains hidden, that the deepest mysteries do not spill outward into chaos. Space-time uses them like knots in a net, holding tension in place so the wider fabric remains strong. And yet, these knots are not final. Black holes evaporate over unimaginable eras, returning their stored information back into the universe through Hawking radiation. Even darkness itself is recycled. Nothing remains trapped forever. There is no absolute prison, only transformation guided by law. Across billions of light years, galaxies spin in harmony, bound together by dark matter, an invisible scaffolding that preserves the cosmic architecture. Without it, structure would dissolve, stars would drift apart, gravity alone would not hold the grand design. Space ensures its own continuity through forces we can detect, but not yet fully understand. Everywhere we look, the universe is doing maintenance. Every limit is a preservation of coherence. Every boundary is a commitment to reality. If we could somehow zoom out beyond the cosmos and observe it from a truly external perspective, we would not see chaos. We would see a system working tirelessly to remain whole. Space-time holds itself together. And so, even as we explore the most powerful objects in existence, black holes, we find that they are not exceptions to natural order. They are the clearest expression of it. They show us the rules by pushing them to their edges. Rotation cannot surpass its limit. Charge cannot exceed its balance. Energy cannot escape its own consequences. These boundaries are not failures of possibility. They are the universe honoring the requirements of understanding. They ensure that what happens in the cosmos has a reason, and that the future cannot sabotage the past. Tonight, As you lie beneath the quiet turning of Earth, these same rules cradle you. Your heartbeat flows forward in time. Your atoms remain stable. Your existence remains anchored to laws that never falter. In a universe of extremes, serenity comes through structure. In a sea of motion, order keeps the waves gentle. In a cosmos full of potential chaos, space-time keeps the rhythm slow and predictable enough for life to exist. This is how the universe protects itself, and how it protects you. As we continue this journey through the quiet boundaries that define existence, another question gently opens like a door at the end of a long hallway. If space-time enforces these limits with such care, then what happens to the energy that pushes against them, the energy that black holes cannot keep forever? Now we drift into Part 7. Part 7. Why energy cannot be infinite. Infinite energy would mean infinite curvature of space-time. The cosmos resists that with every law it possesses. From the Planck scale to galactic structures, limits exist to ensure the universe remains observable and survivable. We often imagine power without end, stars burning forever, galaxies growing larger and brighter, black holes swallowing everything until only darkness remains. But nature does not operate in infinities. It builds steadily, carefully. It allows great concentrations of energy, but never limitless ones. Infinite energy would tear the seams of the laws that hold reality together. It would collapse structure into chaos. It would erase the distinction between before and after. So the universe does something remarkable. It chooses boundaries. Energy shapes space-time. It bends the geometry we move through. It tells matter where to go, guides light in elegant curves. If we add more energy into a region, the curvature deepens, gravity strengthens, until a limit arrives, collapse begins, a star becomes a black hole, pressure becomes singularity. It is the cosmos saying, here and not beyond. These transitions aren't failures, they are safeguards. Black holes are containers for too much energy. They keep the extreme hidden from the rest of the universe, preventing the infinite from spilling outward. Even inside those frozen depths, there is a limit to how extreme conditions may become. If energy density tries to grow without end, quantum rules intervene. The Planck scale rises like a barrier, a final frontier beyond which space-time itself becomes discrete, grainy, and unpredictable. Motion can no longer shrink distances arbitrarily. Curvature cannot deepen into absurdity. Where infinities appear in equations, physics whispers, you have reached the edge of your current understanding. Try a new language. That language is quantum gravity, a theory still incomplete, yet already full of promise. It suggests that there is no such thing as infinite compression, no point of zero size, no place where the laws of nature stop working. Energy cannot become infinite because space-time refuses to collapse without form. Even the universe as a whole honors this truth. Although it is expanding and energy spreads out over increasing distance, conservation laws ensure that total usable energy declines in certain forms. Stars burn through their fuel and fade. Black holes evaporate slowly through Hawking radiation. Photons stretch into longer wavelengths as space expands, losing energy to the cosmic horizon. The cosmos cools with time, growth becomes gentler, motion relaxes into stillness. This serenity is not decay, it is balance. If infinite energy were possible, the Big Bang would have ripped the universe apart instantly. No galaxies, no stars, no time for life to appear. Instead, conditions hovered delicately between expansion and collapse. Gravity slowed the initial explosion just enough to allow structure to form. Dark energy later stepped in to accelerate the expansion, but not too violently, not too soon. Existence is a careful equilibrium. Even on the tiniest scales, particle physics prevents runaway energy. When high-energy particles collide inside particle accelerators, new particles splinter into existence, but only those allowed by strict conservation laws. Symmetry governs every reaction. A kind of accounting is always present. Nothing from nothing, nothing into nothing, always transformation. Energy moves, shifts, changes form, radiates outward, but never exceeds the cosmic budget. Even the idea of temperature, heat as a measure of energy, has an upper bound. Physicists call it the Planck temperature, beyond which heat would tear apart the intellect of physics. Matter cannot exist in recognizable form there. The universe itself would boil into something without pattern. And so, no phenomenon in nature has ever reached this temperature. Not even the cores of supernovae, not even particle collisions in the early universe after the Big Bang's first instant. Infinity is avoided at every turn. Astronomers observe the universe not as a story of unbounded escalation, but as one of powerful but regulated evolution. Giant stars can only grow to a certain mass before their own radiation blows away the very gas that feeds them. Galaxies merge and transform, but their brightest cores, the supermassive black holes, self-regulate through feedback, jets of energy pushing outward, preventing infinite growth. Energy rises, gravity responds, equilibrium returns. You too are part of this. The energy in your body, stored in chemical bonds and electrical signals, is finite, measured, gentle. If your atoms held infinite energy, they would explode outward. If mass grew unchecked, you would collapse inward. But instead, balance safeguards your existence. The quiet truth is this: a universe without limits could not host life. Limits allow structure, structure allows complexity, complexity allows consciousness, and so the cosmos, vast beyond comprehension, survives by preventing its own extremes. When we speak of infinite energy, it is tempting to imagine unlimited potential. But physics teaches a softer wisdom, that boundlessness is not freedom, but destruction. It would remove the possibility of distinction, of identity, of form. Without limits, there is no shape to existence. The universe seems endless because it hides its boundaries behind horizons, the edges of black holes, the walls of the cosmic light speed limit, the invisible thresholds where quantum rules shift the game. These boundaries are not cages, they are foundations. There is peace in the knowledge that nothing can become too much, that collapse cannot swallow all, that the extremes remain contained. Tonight, as you drift deeper into calm, the energy that fuels your breath is ordinary, beautifully ordinary. And that is why you are here. That is why you are safe. That is why the universe feels quiet enough to dream. What lies beyond our sight, black holes, collapsing stars, cosmic violence, all obey the same gentle ceiling. Power is immense, but never infinite. Darkness is deep, but never bottomless. The universe guards itself from the impossible. And as we continue this silent journey, a question begins to rise from all this balance and restraint. What happens when a black hole reaches for the highest power allowed, and space-time answers with one final graceful transformation? Now we drift into Part 8. Part 8. The fate of a black hole at the limit. As a black hole approaches the ultimate spin or charge, strange things happen. Space around it twists, light orbits in delicate loops, and the slightest additional push triggers balance, radiation, ejection, gentle loss, the cosmos choosing stability over chaos. Black holes may be the most extreme objects in existence, but they are not reckless. They walk the razor edge of physics, where every motion, every shift of energy must obey the quiet laws that preserve the structure of reality. When they grow too ambitious, spinning too fast, charging too strongly, space-time itself intervenes. The universe never allows a black hole to push past the threshold into disorder. To watch one approach its limit would be like watching a dancer lean toward the very edge of a cliff. There is grace, but also a pullback to safety, a subtle correction with every breath. Let us begin with rotation. As a black hole spins faster, it drags space-time with it, a swirling whirlpool of gravity where nothing can remain still. The region where this drag dominates is called the ergosphere. Within it, even light has no choice but to spin along with the black hole's rotation. The faster the rotation, the larger this region grows, like a storm swelling as energy builds. Approach too close to the rotational limit, the The Kerr limit and the nature of the horizon changes. It thins, it stretches, it becomes fragile, as though the fabric of spacetime is pulled too tight. The closer it gets to the maximum, the more actively the black hole resists further acceleration. It pushes away the very energy that feeds its spin. Try to give it more angular momentum, and energy will fling outward in a brilliant jet of radiation. Magnetic fields tangled in the swirling disk around the black hole can tap into the rotation itself, launching twin beams into the cosmos, long pillars of light and plasma that extend for galaxies. The power of these jets is astonishing, but their purpose is simple: to reduce the black hole's spin, keeping it below the edge, the same quiet. Moderation governs charge. A black hole collecting too many like-charged particles begins to repel further arrivals. Electromagnetic forces push outward with increasing strength, standing firm against collapse. If the imbalance grows large enough, the electric field near the horizon becomes so intense that the vacuum of space breaks open. Pairs of particles burst into existence, opposites rushing inward to neutralize the excess, like charges fleeing in streaks of radiation. The black hole's greed for charge becomes impossible. Nature denies perfection. So what truly happens when a black hole reaches its brink? It does not break the laws of physics. It adheres to them more closely than ever. The behavior of spacetime becomes elegant, a perfect equilibrium. In this near-extremal state, the event horizon cools. It approaches a temperature of absolute zero, motion frozen in time. The horizon's surface becomes smooth and minimal. Its geometry tightens into a shape defined solely by symmetry. Time stretches deeper. To an outside observer, the plunge toward the horizon takes longer and longer, the flow of time slowing toward stillness. The whole becomes maximally efficient. It can store the most possible information in the smallest possible surface. It is the universe achieving balance at the edge of its own potential. But this balance remains delicate. Any addition of energy, even the slightest, triggers a recoil. A particle with the wrong spin direction may be rejected outright, flung back into space. A stray charge may spark a burst of radiation that robs the whole of what it tried to take. A collision with a companion star may create turbulence that slows the dance. The black hole remains powerful, but humbled. In these moments, it becomes clear that black holes are not engines of destruction. They are regulators. They keep the cosmic books balanced. Even when two black holes merge and space-time rings like a bell, the result is not catastrophe. Instead, the new black hole's spin is always lower than the maximum allowed. It sheds energy through gravitational waves, keeping the horizon intact. The universe protects itself through these vibrations, soft reminders that order must prevail even in collision. Energy leaves, spin slows, charge dissipates, balance wins. And this quiet enforcement of limits has profound consequences for the universe. Galaxies remain stable, stars can form without being torn apart. Time keeps a steady direction. Causality remains intact. Without such restraint, a single naked singularity could rewrite the rules of physics everywhere. One exposed infinity could collapse the meaning of distance, erase the sequence of events, and render the universe unknowable. But the horizon holds firm. The secret remains hidden. Even inside a black hole, the laws of physics respect the limits set by spacetime. Though we do not yet know fully what happens at the singularity, theories suggest that quantum gravity steps in, preventing infinite compression, replacing the predicted point-like center with a region of finite structure. Limits upon limits. Protection upon protection. It may seem strange that the universe must guard itself so carefully, but that careful stewardship is the reason there is structure at all, the reason galaxies spin calmly, the reason stars shine on predictable lifetimes, the reason you can breathe in rhythm with the turning Earth. As you lie here, still and quiet, you are held gently by the same laws that moderate black holes. The cosmos is vast and powerful, but never careless. It chooses stability over chaos, always. And so, when a black hole approaches the threshold of what is allowed, it finds a way to step back. Not because it knows the danger, but because space-time itself will not permit anything else. Even the most extreme objects in existence are shaped by rules, rules that preserve consistency and reality itself. As we continue drifting deeper into this calm understanding, another curiosity begins to rise. If a black hole can never hold infinite power or reach impossible speed, and if it must always share what it cannot keep, where does all that energy go? Now we drift into Part 9. Part 9. The Planck Wall. The Final Scale. There's a smallest length with meaning, the Planck length, where space-time becomes turbulent and unpredictable. If a black hole shrinks close to this, the universe's granularity itself steps forward, preventing further collapse into the undefined. This is the frontier where the familiar picture of reality dissolves. Our everyday world feels smooth. Time flows cleanly, distance stretches continuously, motion is a gentle glide from one point to another. But beneath that illusion lies something deeper, something far less certain. Space-time, at its foundation, appears to be made of finite steps, tiny units so small they cannot be divided further, without losing meaning. That distance, about 1.61035 meters, is called the Planck length. If you could shrink to that scale, atoms would appear impossibly vast. A proton would tower over you like the entire known universe. And yet, this is the scale where quantum gravity, the unification of quantum mechanics and general relativity, is thought to reside. Here, smooth curvature becomes a storm. Time trembles, geometry flickers, space-time becomes a restless ocean of creation and collapse. Physicists call it quantum foam, the jittering chaos from which the calm surfaces of space and time emerge. But this foam cannot be probed directly. Any attempt to observe such tiny distances requires energy so great, the act of observation collapses the region into a black hole. The universe hides its smallest truths behind the very darkness they create. This is the Planck Wall, the final boundary of measurement. Black holes, for all their hunger, can approach this scale only at the very end of their lives. When a black hole consumes matter and grows, its horizon expands. But as it radiates energy away, shrinking slowly through Hawking radiation, the horizon contracts. The curvature increases. Space-time begins to tighten and strain. As a black hole evaporates, its temperature rises, the opposite of what we expect for ordinary objects. The smaller it becomes, the hotter it grows, until the radiation pouring from it becomes violent and unstoppable. The pace of evaporation accelerates. A quiet, ancient giant becomes a furnace in its final heartbeat, and the horizon approaches the Planck scale. But there, evaporation must stop. There, the rules change. Because to shrink further would mean collapsing space-time into a point of infinite density, a true singularity, an idea the universe refuses to allow. Quantum physics intervenes, gravity hesitates, the collapse slows into uncertainty. Many physicists believe the black hole does not simply disappear. Instead, it reaches a stable, compact form, a Planck-sized remnant, a smallest possible kernel of gravity and information, a place where the entire history of what fell inside remains encoded, compressed into the tiniest structure nature permits. Others believe something even stranger, that the core of a black hole may never become a point at all. Instead, quantum gravity might replace the singularity with a region of extreme but finite density, a bubble of space where collapse rebounds. In this view, a dying black hole might someday burst into a new universe, expanding outward with its own Big Bang, hidden from us behind an event horizon until the moment of release. Whatever the truth, the Planck length stands as a quiet guardian, a measurement beyond which our current mathematics cannot pass. It is the cosmos saying, you may come this far, but no further with the tools you have now. Even our language struggles with these ideas. We speak of length and time as if they are infinitely divisible, but the Planck scale tells us that nature has a minimum pixel size. Below it, distance is not smaller, it is simply undefined. Time does not tick faster, it loses meaning entirely. Imagine a painting so detailed you believe it continuous, until you place your eye so close you see the individual points of pigment. The Planck scale is that closeness, the pixels of existence. The equations that describe planets and stars cannot survive this resolution. Even the mathematics of particles and forces, the realm of quantum physics, begins to falter. Only a new framework, a truly unified theory of gravity and quantum mechanics, can explain what lies beneath. The universe protects its deepest secrets until we earn the right to understand them, and black holes, in their final stages, become the testing ground. They are the universe's laboratories for the Planck scale. Extreme gravity compresses matter and energy into a realm where classical physics breaks down. They push our theories to their breaking points and teach us where the answers are missing. Yet even as black holes reach for that smallest boundary, they do not tear the fabric of space-time. They do not expose the undefined. Instead, quantum laws shape a softer landing, a limit, a minimum size, a final resting place where the unknown remains contained. There is safety in that boundary, stability in mystery. If we could peer through that last veil, perhaps we would find the blueprint of reality itself, the code from which all space and time emerge. But for now, the Planck wall guards it silently. You might imagine this wall as harsh and unwelcoming, but it is the reason the universe is gentle enough for life. Without a smallest scale, infinities would roam free. Singularities would spill into the cosmos. Causes and effects would blend into uncertainty. Nothing would be predictable. Nothing would be safe. Limits create order. Order allows stars to shine. Stars create the elements that form living beings. Every breath you take relies on the existence of this final frontier, the ultimate scale that keeps impossibilities hidden so the possible can flourish. As you lie here tonight, the Planck length is everywhere beneath you, in every particle, every wave, every heartbeat. You are built upon structured limits so fundamental that they shape the very meaning of existence. Black holes may roar against those limits, but the universe always answers with calm restraint. And as we glide forward on this quiet cosmic voyage, a new question rises from the darkness at that smallest boundary. If black holes must one day give up the energy they hoard, what happens to the hidden information they once consumed? Now we drift into Part 10. Part 10. Why information must survive. The universe guards knowledge, not out of sentiment but necessity. Even when consumed by a black hole, information is not destroyed. It is transformed, encrypted, preserved at the horizon. Energy limits help ensure that nothing is truly erased. In physics, information is not just facts or memories. It is the complete description of the physical state of a system. Every particle's position, every motion, every quantum detail that makes something what it is in a given moment. If information could vanish, the universe would lose its ability to remain consistent. Cause and effect would fray. The past would dissolve into nothingness. And so, nature has a strict rule: information cannot be destroyed. Yet black holes challenge that principle more than anything else in existence. When matter falls into a black hole, it disappears behind the event horizon, seemingly swallowed forever. At first glance, the story ends there. The details of what fell in are lost, replaced by only 3 numbers that describe the black hole itself: mass, charge, spin. This is the no-hair theorem, a poetic way of saying that black holes reveal nothing about their contents: no texture, no past, no individuality. A star, a planet, a library, a person, all reduced to the same quiet numbers. It's a troubling idea, because it looks like information simply vanishes. Stephen Hawking called this the information paradox. If black holes erase information, then physics loses its foundation. The universe would no longer conserve meaning. Time itself would unravel, because without memory, what distinguishes one moment from another? The cosmos cannot allow such a void. So the black hole does something remarkable. It preserves information on its surface, the event horizon, in a subtle encoding we do not yet fully understand. This idea, that the information is stored on the boundary rather than inside, led to one of the most groundbreaking concepts in modern physics: the holographic principle. The universe may store its deepest truths like a hologram, information spread over a surface, not buried in volume. Just as a 2D hologram can hold a 3D image, the event horizon holds the imprint of everything that falls within, or nothing escapes, except memory. But the memory is scrambled into patterns almost impossible to decipher, the black hole's own language of secrecy. It is not destruction. It is encryption. Hawking radiation carries this idea further. Black holes evaporate, slowly, over astronomical ages, shedding energy in the form of tiny particles. For decades, Hawking believed this radiation was random, devoid of information. If so, once a black hole evaporated completely, its secrets would be gone forever. But newer research suggests something more hopeful. The radiation may carry information outward, piece by piece, a slow unspooling of the black hole's internal story. Over vast epochs, nothing is forgotten. Like a book written in a language nobody yet understands, the black hole broadcasts its history back to the cosmos in a code of heat and light. Information may be delayed, but it is never destroyed. This principle connects black holes to every scale of the universe. In quantum mechanics, particles exist not just as objects, but as carriers of information. When two particles become entangled, they share a bond that acts like a communication of identity, a reminder that what happens to one still matters to the other. That connection, too, cannot be erased. Even when particles vanish from existence, annihilating into light, their information is carried on in the photons, their quantum imprint woven into the next form of energy. Everything transforms. Nothing is lost. On the largest scales, galaxies merge, stars collapse, planets come and go, yet the total ledger of information remains intact. Conservation is not merely a law of physics. It is a promise that the universe keeps to itself. It is the foundation of memory, not just biological memory, but cosmic memory. It ensures the story of the universe can be told from start to finish without missing chapters. As you breathe gently now, every cell in your body holds information that has survived every transformation since the dawn of time. The atoms in your hands were forged in ancient stars, carrying the imprint of nuclear processes billions of years old. The carbon in your DNA holds patterns shaped by Earth's earliest oceans, passed through generations without erasure. You are a vessel of universal memory. Even your thoughts, the fleeting electric signals in your brain, are part of the fabric of information. They move through neurons, recorded in subtle changes to connection strength, leaving traces that time cannot fully erase. Long after each moment passes, its information persists in the structure of the world. This is why black holes must follow the rule. This is why horizons cannot tear. This is why nothing truly falls into oblivion. If information could disappear, the universe would lose its continuity, its logic, its identity. There would be no reason for anything to unfold the way it does. No anchor to time, no record of existence, but instead, the cosmos honors every detail. Black holes, the darkest archives of reality, store knowledge with profound efficiency, their surface area determining exactly how much information they can contain. Not volume, surface, because the universe protects its history at the boundary, where we might someday read it again. Tonight, the information that makes you who you are, every memory, every decision, every molecular shape, is held in place by the same laws that preserve the secrets of black holes. You are safe within a universe that refuses to let knowledge vanish. The deepest truth of Part 10 is simple, gentle, and enormous. Information is the thread that holds the tapestry of existence together. As long as information survives, the universe remains whole. And so, as we continue drifting through these quiet cosmic boundaries, one question now calls softly from beneath all this order. If black holes must preserve information, what happens to the energy they slowly release, the light they whisper back into the universe over time? Now we drift into Part 11. Part 11, Hawking Radiation, the Quiet Release. Black holes evaporate, slowly, quietly. Over trillions of years, their energy leaks outward as soft whispers of particle light. This evaporation prevents any black hole from becoming eternal, a final limit on even the darkest objects. A black hole may seem like the ultimate place of no return, a prison where light and matter fall inward forever. Yet even this fortress of gravity cannot keep its power locked away. At the very edge of the event horizon, a delicate process unfolds, one that Stephen Hawking uncovered through careful thought and quiet courage. In the emptiness of space, particles flicker into existence. This isn't creativity, it is uncertainty. Quantum laws allow pairs of particles to appear spontaneously as long as they reunite and disappear quickly enough. Normally, these pairs cancel each other out, leaving behind no trace. But near a black hole, the story changes. One of these particles may fall inward, lost to the singularity, while the other escapes outward into the universe. That escaping particle carries a tiny bit of energy, and energy, as we have learned, is mass. When a particle leaves, the black hole grows just a little bit smaller, like a long, slow breath drawn out across the ages. This outward trickle is Hawking radiation, a release so gentle it would take longer than the current age of the universe to notice it in a massive black hole. But it is relentless. Quiet persistence is part of its nature. The larger the black hole, the slower its evaporation. The smaller the black hole, the faster it fades. When a black hole shrinks, its temperature rises, its glow brightens, its whispers become sparks. At the end of its life, evaporation accelerates dramatically. A black hole that has existed serenely for trillions of years may end in a final flare, one last flash of energy into the darkness. A farewell. This process changes how we think about black holes completely. They are not eternal predators. They are temporary structures, guardians of their own boundaries, but still subject to change. Even darkness must age. This slow release carries consequences, because each photon emitted from the event horizon carries a fragment of information about what once fell inside. The radiation is not random after all. It holds a subtle encoding of the universe's past, restoring the balance of knowledge over time. What looked like destruction becomes transformation. A black hole, once thought to erase the cosmos's history, becomes instead its silent archivist, a keeper of secrets forced to share them eventually. This is why the horizon matters so much. It is the interface, the membrane that negotiates between inner mystery and outer clarity. Hawking radiation reminds us that the flow of the universe is never one way. What is taken must be returned. Black holes reshape the cosmos, but they do not deprive it. Their very existence depends on the ability to eventually let go. This evaporation connects to something deeper, the idea that nothing in the universe can hoard infinite energy. If a black hole could hold its power forever, it would become a frozen monument of mass, sealed off from the cycle of creation and transformation. Eventually, so much matter would fall inward that the universe's future would tilt toward collapse. Instead, Hawking radiation guarantees cosmic renewal. Energy returns to space. Starlight once swallowed finds a new path outward. Across unimaginable stretches of time, this gentle glow participates in the story of change. Picture a black hole alone in the far future, long after stars have burned out and galaxies have drifted apart. The cosmos is a colder, darker place, but somewhere deep in that void, a black hole still radiates, slowly unraveling its enormous mass into scattered particles. The last lights of the universe may be the quiet embers of evaporating black holes. This thought is not sorrowful. It is serene. Even when the cosmos reaches its final chapters, nature continues to work with purpose, preserving structure, honoring conservation, letting nothing stagnate in absolute silence. The universe is always in motion, always releasing and renewing. There is beauty in the patience of Hawking radiation. Beauty in the idea that power must eventually diffuse, not dominate. Beauty in the promise that even the most unbearable density softens with time. In a sense, black holes do not die, they finish their task. They compress, they store, they protect the forbidden edges of physics. and then, when all is balanced, they dissolve into light again. Their disappearance completes the journey of matter, from brilliance to collapse to quiet rebirth. The evaporation of black holes also reassures us that extremes are temporary. A universe dominated by darkness is not our fate. The rules that shape existence ensure that light and knowledge are never permanently confined. Every secret leaves eventually. Every hidden moment finds expression. Every trapped photon becomes free. Even now, as you sit in calm quiet, Hawking radiation flickers at the edges of spacetime, far beyond sight, yet deeply real. It is a reminder that nothing lasts forever, and that this truth is gentle, not harsh. Change is universal. Release is necessary. Balance is destiny. As we rest in the safety of these cosmic laws, one more question rises softly from the edge of the horizon. If the universe hides its deepest singularities behind horizons, why is it so committed to keeping them hidden? What principle ensures that no singularity ever stands exposed, that reality always remains protected from what lies beneath? Now we drift into Part 12. Part 12. Cosmic Censorship, a Promise in the Yi. Dark physics predicts something profound. No observer should ever see a naked singularity. Spacetime hides its most extreme truths behind horizons, enforcing a cosmic censorship that preserves causality, order, and reality. A singularity is the most mysterious object imaginable, a point where density becomes immense, where the curvature of spacetime rises without bound, and where our existing laws of physics fall silent. It is the place where questions deepen into paradox, where time and space lose their familiar meaning. Yet, despite this, singularities form often. They form in the hearts of collapsing stars. They may exist at the core of every massive galaxy. They are mathematical consequences of gravity's immense power. So why have we never seen one? Why does every singularity in nature remain hidden, concealed behind the dark boundary of an event horizon? This is the quiet promise of cosmic censorship. The universe refuses to expose its deepest contradictions. When infant's singularity were laid bare, open to the cosmos, the consequences would be extraordinary. Light paths could break, information could travel backward in time. The laws that define motion, identity, and truth might dissolve into uncertainty. Cause could lose its place before effect, order could unravel, reality could lose coherence. So the universe shields singularities within black holes, like fragile secrets cradled inside a protective shell. The horizon is more than a boundary. It is a veil guarding the integrity of physics. We do not yet know the full reason this censorship exists. It is not a rule we imposed. It appears to be a law the universe created for itself, a promise to prevent contradictions from cascading outward. Even when a black hole approaches extremes, too much spin, too much charge, the horizon defends itself. It widens, emits radiation, or sheds angular momentum. Every attempt to expose a singularity is met with subtle correction. Spacetime steps in. It refuses to reveal the unfiltered core. This is not a denial. It is a protection of consistency. Imagine if even a single singularity stood naked to the cosmos. It would reveal a place where the known laws of physics break down completely. We could no longer trust the future to follow from the present. Predictability, the most foundational trait of science, would falter in the face of chaos. The universe would no longer be readable. And so, cosmic censorship works silently, everywhere. No alarms, no warnings, simply quiet prevention. It is astonishing how deeply this principle shapes the cosmos. Stars can collapse without threatening causality. Galaxies can orbit around hidden singularities without disorder. Gravity can reach unimaginable intensities, safely contained. The very existence of structure depends on this restraint. Even when black holes collide, some of the most violent events in the universe, the aftermath remains shrouded. The singularities within never touch the outside world. Instead, they merge behind a freshly formed horizon, the final shape smoothing away any hint of chaos. The gravitational waves we detect are filtered, elegant echoes, the universe's version of telling us just enough. We see what space-time chooses to show, nothing more. This protection does not stem from fear, but from necessity. The laws of physics are not just tools of prediction. They are the scaffolding that allows the universe to exist as a place of consistency and meaning. A singularity without a horizon would risk dissolving that foundation. Cosmic censorship ensures that the mysteries remain quietly contained until we are ready, not just technologically, but theoretically. Perhaps one day new physics, quantum gravity, a deeper unification, will transform our understanding. Maybe singularities are not truly infinite. Maybe they are gateways to new structures. Maybe they are the seeds of future universes. But until we understand, the veil remains in place. There is kindness in this ignorance, safety in the darkness. Consider how delicately balanced this protection is. Black holes push the boundaries of physics. They stretch space-time to its limits, but never snap the thread. Every extreme is buffered, every abyss is locked, every secret remains whispered. Cosmic censorship is a promise that the universe will never betray itself. A promise that knowledge will remain coherent. A promise that time will not tear. You, simply by existing, benefit from this vow. Your memories remain meaningful because cause leads to effect. Your perception of time remains linear. Your world remains grounded in structure. If singularities were exposed, the stability of existence would become fragile. Everything could become unpredictable. Yet instead, we exist in a cosmos where change flows smoothly, where the deepest unknowns are locked gently behind horizons of shadow. As you rest tonight, remember that safety does not come only from the familiar. It comes also from what is kept hidden. The universe is full of mysteries so powerful that their revelation could unmake the laws that support life. Instead of unleashing them, space-time lets them remain in silence. The horizon is a kindness. Cosmic censorship is not a barrier against discovery. It is a quiet placeholder, a message waiting to be decoded once we evolve the language to interpret it. Black holes are not prisons for truth. They are libraries with restricted access, holding knowledge until the universe determines we can read it without collapsing the narrative. Nothing is forbidden forever, only protected until its time. Even now, new theories and experiments bring us closer to understanding what lies beneath the horizon. Mathematical models suggest pathways into the quantum core. Researchers imagine that singularities may be replaced with finite structures, loops, layers, knots in space-time. Perhaps there is no true destruction beneath the horizon, only transformation. But cosmic censorship remains firm for now. A quiet promise honored by every black hole in existence. The singularity waits, the horizon watches, the universe remains calm. And as we continue on our peaceful journey through the laws that hold all of this together, a question begins to glow softly at the edge of our curiosity. If singularities must remain hidden, how does the universe keep track of everything inside them? How does it measure meaning in a place without time? Now we drift into Part 13. Part 13. Entropy at the edge of gravity. The surface of a black hole, the event horizon, encodes its entropy. The more massive the hole, the greater its surface and the more information it can store. But even this has limits. There's a maximum to how much complexity can hide in darkness. Entropy is often misunderstood. It is not chaos or disorder in the casual sense. In physics, entropy is the measure of how much information a system contains that we do not know. It counts the hidden details, all the microscopic configurations that could produce the same outward appearance. The higher the entropy, the more possibilities lie beneath the surface. A star is full of data. The fusion reactions within, the magnetic currents, the structure of atoms. When it collapses into a black hole, you might expect that complexity to vanish. But the universe does not allow information to disappear. Instead, it stores all that hidden detail in the horizon, in the very area of the black hole. Jacob Bekenstein first recognized this deep truth. A black hole's entropy is proportional not to its volume, but its surface area. This idea was shocking. Surface area, not volume. The skin of the black hole holds the story of everything inside it. Stephen Hawking soon contributed the crucial piece. Black holes radiate. They possess temperature and entropy like any physical object. His calculations gave us the formula for black hole entropy. The area of the horizon measured in units of the Planck length squared. Each tiny patch of surface, each Planck-sized pixel, can store about 1 bit of information. The horizon becomes a tapestry of memory. Every patch a symbol, every symbol a piece of the universe's history. This discovery changed physics forever. It hinted that reality itself might be holographic, that all the information contained in a region of space might be describable by the surface that surrounds it. A lower dimensional boundary encoding a higher dimensional world. A black hole is the most extreme example of this principle. It is an object where the laws of the cosmos are forced to reveal their underlying efficiency. But the horizon can only grow so big. Its surface is finite, and therefore, so is the information it can store. If a black hole grows, the horizon expands, more surface area, more entropy, more capacity to store the past. But if evaporating radiation shrinks it, the storage space diminishes. The compression of entropy becomes intense, a fight against the cosmic prohibition of information loss. This balancing act is delicate. It ensures that the black hole never becomes overwhelmed and never loses track of its memory. Entropy may sound abstract, but it touches everything we know. The aging of stars, the melting of ice, the spread of heat, the direction of time itself. We experience entropy as the flow from order to disorder, from structure to simplicity, from usable energy to background heat. It is why time feels like movement forward, not backward. Every second, entropy grows just a little bit more. Black holes accelerate this growth. They are the endpoints of gravitational complexity, the final resting places of matter's structured past. Yet, inside a black hole, structure becomes invisible. Entropy rises silently as the horizon expands. Imagine all the possibilities contained in a star before it. Collapses. The swirling plasma, the nuclear reactions, the history of its formation. When the star falls inward, those possibilities do not vanish. They are translated into patterns on the surface of the horizon, invisible to us, yet preserved. Entropy tells the universe nothing is forgotten. But entropy also sets a limit. The more information a black hole stores, the more surface it needs. There comes a point where no further compression can occur without breaking the rules of physics. The horizon cannot shrink below the Planck scale. The entropy cannot exceed the capacity of its area. Even darkness must respect its storage limit. This boundary protects the universe from extremes of complexity. If information could be packed infinitely tight, the cosmos would be vulnerable to instability. A single point containing infinite knowledge could distort space and time unpredictably. Instead, entropy ensures that information remains distributed, spread across surfaces, manageable, structured. In every black hole's surface, we see a quiet compromise. Collapse without erasure. Simplicity without ignorance. Darkness without losing truth. The more massive the black hole, the more serene this balance becomes. Supermassive black holes, hundreds of thousands to billions of times the mass of our sun, act as enormous vaults. Their horizons calm and wide, able to store staggering amounts of entropy. But they too have limits, a maximum defined by the area of their event horizons. The cosmos refuses infinite memory inside finite space. Even the universe as a whole obeys an entropy budget. Galaxies forming and fading, stars igniting and cooling, matter cycling through birth and death. The total amount of usable energy decreases, but the total amount of information increases, locked into structures we can no longer access directly. Black holes are the archives of this growing mystery. Entropy is why time has direction. It is the push from what was to what must be. The universe is always writing new chapters, and black holes are its deepest libraries. When you look up into the night sky, every star's glow is a message. Energy becoming entropy, memory expanding in complexity. And when those stars collapse, their stories do not end. They move inward, written into a horizon that no eye can see, yet no law can erase. The atoms in your body carry entropy, information about billions of years of cosmic evolution, patterns inherited from ancient stars. In your existence lies proof that the universe remembers. Entropy ensures continuity. Entropy ensures causality. Entropy ensures that tomorrow will not rewrite yesterday. And black holes, occupying the edge of what is possible, show us that even the deepest darkness honors the sanctity of knowledge. They do not delete the cosmos, they catalog it. As you rest tonight, wrapped gently in the flow of time, entropy is the reason you feel grounded in the present. It is the reason your memories have meaning, the reason you experience motion from past to future. In the calm boundaries of black holes, the cosmos keeps this rule intact. No matter how extreme the gravity becomes, the details of what fell inside are preserved somewhere, encoded in silence. Entropy, like a soft librarian, guards the universe's history. And as we continue forward, a new thought emerges quietly from this understanding. If entropy grows on the horizon, if every black hole preserves the complexity of what it consumes, then what does this say about the universe itself? Could the cosmos be defined by the same balance, held together by quiet limits that prevent chaos from overwhelming structure? Now, gently, we drift into Part 14. Part 14, the universe's balance between chaos and calm. Energy pushes, gravity pulls, rotation tries to run away. Space-time guides them all back into harmony. The universe is not built for excess. It is built for balance. Every limit is a puyi, whisper of equilibrium. Even from the earliest moments after the Big Bang, balance has been the quiet architect behind everything that exists. The cosmos expanded with extraordinary speed, yet not so fast that matter flew apart too quickly for galaxies to form. Gravity gathered that matter into luminous clusters, yet not so forcefully that all things collapsed back into a singular knot of darkness. This exquisite balance continues everywhere we look. Stars burn because nuclear fusion and gravitational weight are locked in a delicate standoff, pressure pushing outward, gravity pulling inward. If fusion dominates, a star explodes. If gravity wins, it collapses. But for billions of years, many stars exist in a peaceful equilibrium, shining with steadiness, supporting the possibility of life. Planets orbit because velocity and attraction are perfectly matched, motion bending into a circle that never falls inward and never escapes outward. Even in chaos, orbits evolve, slowly, gracefully adjusting over time. And black holes, the most extreme engines of nature, honor these same boundaries. Their existence is not a story of excess, but of control. They rotate, but not beyond a limit. They hold charge, but not infinitely. They compress matter, but never to the point where space-time becomes meaningless. Balance prevents breakdown. Balance preserves existence. Balance is the quiet geometry of reality. We often imagine chaos lurking beneath everything. Storms in atmospheres, supernovas in galaxies, collisions in the cosmic dark. And yet, beneath every turmoil, balance pulls the strings invisibly, restoring order the moment extremes threaten to overrun stability. Galaxies collide, but they settle into new spirals. Stars collapse, but they become black holes whispering light into space. Energy transforms, but never vanishes. Chaos becomes calm. Calm holds together the story of the cosmos. Space-time itself carries out this constant moderation. Einstein's equations do not allow runaway acceleration or impossible forces. They tie energy to curvature. Mass shapes geometry, and geometry guides motion. Everything influences everything else, never alone, never unchecked. A black hole is not an act of destruction. It is the minimum shape needed to store too much energy. A safeguard carved from gravity. Extremes are not forbidden. They are simply guided into forms that keep the cosmos coherent. The early universe could have unraveled into smooth emptiness. No galaxies, no stars, no life. or it could have collapsed instantly under its own weight. Instead, fundamental constants, the strength of gravity, the charge of the electron, the speed of light, landed in narrow ranges where structure can flourish. The universe chose balance over extremity. Particles feel quantum uncertainty, a rule preventing perfect precision. This tiny randomness keeps atoms stable, preventing electrons from spiraling into nuclei. Imperfection is the foundation of endurance. Even temperature and entropy honor boundaries. Heat flows from hot to cold, energy spreads out, and the universe coasts toward stillness, yet never in a way that erases the past. Entropy ensures evolution, but not collapse into total sameness. Memory survives in the patterns that remain. Everywhere we look, limits protect meaning. As black holes remind us, when energy accumulates too intensely, collapse gives rise to structure, a new boundary that preserves what lies inside. And when that structure grows too oppressive, evaporation distributes its power back into the universe. Growth, pressure, collapse, release, over and over again. Balance is not a static thing. It is motion under control. It is change made predictable. On cosmic scales, this plays out over billions of years. On human scales, it unfolds in each breath. Your lungs inhale until fullness urges release. Your heartbeat balances pressure and rest. Even your thoughts drift between focus and calm, between order and imagination. You are a moment of equilibrium in a universe ruled by symmetry. The laws that govern galaxies also shape the quiet chemistry of your cells. The geometry that defines black holes guides the motion of blood through veins. Balance is not just the nature of the cosmos, it is the nature of you. Even time participates in this rhythm. We feel its forward flow as progression, yet entropy ensures that the future remains compatible with the past. The arrow of time points gently, not violently, allowing growth instead of fracture. Black holes, paradoxically, protect the calmness of chronology. They take in complexity but return it gradually, ensuring the cosmic narrative cannot be torn apart by the impossible. Everything that exists plays a role in this cosmic choreography. Dark energy stretches space, dark matter anchors structure, gravity sculpts motion, quantum rules shape stability. Nothing dominates, nothing is ignored. The universe allows chaos, but always tames it into form. Perhaps this balance is what allows consciousness to emerge, an awareness delicate enough to perceive both stillness and motion, both calm and awe. You exist at the intersection of cosmic quiet and cosmic power. Tonight, as you settle deeper into rest, remember that the universe is not a battlefield between extremes. It is a negotiation, a gentle conversation between forces that could destroy each other, if not for the rules that bind them. Without balance, stars would not shine, atoms would not form, black holes would tear the fabric of reality, time would not flow, life would not begin. The beauty of existence lies not in chaos and not in total control, but in the quiet place between. The cosmos is full of unimaginable power, energy beyond comprehension, gravity capable of folding space, yet everything remains guided, ordered, purposeful. Every black hole is a promise that even the deepest distances remain governed by equilibrium. Every star-eyes is a reminder that collapse can give birth to light. Every moment is a testament that the universe allows itself to change only in ways that preserve continuity. Balance is the ultimate limit, the quiet law that ensures we wake each day in a universe that still makes sense. As we drift further into this exploration, one final question rises softly from the harmony we have uncovered. If the universe enforces such careful limits, what does it mean for the future of black holes? What awaits them once balance has run its course? Now we turn the page gently and drift into Part 15. Part 15. The law nothing can break. The cosmic speed limit, the maximum spin, the upper bound of charge, the containment of entropy. Together they reveal a universal truth. Power must always respect structure. Even a black hole, a titan of collapse, is held softly by the boundaries that make space and time possible. Every limit we have explored up to this point, every boundary the universe enforces, points to one simple and elegant philosophy in nature. No phenomenon can wield more power than space-time can contain. This is not a punishment, it is a design. There is a quiet kindness in this law, a guarantee that the universe will not drown itself in its own intensity. Even the strongest forces are guided back into balance, never allowed to run wild and uproot the order that supports existence. Imagine a cosmos with no limits. Stars could spin themselves apart in an instant. Particles could accelerate beyond comprehension. Energy could condense infinitely into a single point. Information could disappear into true nothingness. Time could fold and twist until history lost coherence. In such a universe, structure would be impossible. Meaning would be impossible. Life would be impossible. So the universe sets boundaries, not as prison walls, but as architecture. The speed of light protects causality, ensuring events unfold in a meaningful sequence. Rotation limits protect horizons, ensuring singularities remain hidden and reality remains navigable. Charge limits ensure gravity can always contain collapse. Entropy limits ensure that complexity persists without overflowing into violent instability. Each limit is not a barrier against greatness, it is the reason greatness exists. Black holes are the ultimate expression of this principle. They push every physical law to its extreme, but always stop at the very edge, the final safe line drawn by space-time. A black hole can spin, but only to the Kerr limit. It can hold charge, but only to its Reissner-Nordstrom maximum. It can compress matter, but not beyond the Planck scale. It can store information, but only on its horizon surface. It can accumulate energy, but only temporarily. Evaporation will return it. Even the most powerful object in the universe must bow to structure, and in that obedience it becomes beautiful. These cosmic laws are more than equations. They are the scaffolding of everything that feels familiar. They create symmetry. They prevent infinite chaos. They give existence a stable foundation on which to build stars, galaxies, and consciousness. We live in a universe that respects balance above all else. Even time itself reflects this agreement. The arrow of time, defined by entropy, ensures that events unfold in a direction that does not break the logic of cause and effect. Entropy grows, and with it, complexity and history. Time moves forward because the universe will not allow its story to collapse into nonsense. We tend to think of laws as cold and mechanical. But here, we find something softer, a philosophy of protection. The cosmos is not chaotic at its core. It is precise, harmonious, quietly compassionate with its limits. The most extreme objects in nature, black holes, demonstrate this compassion by existing at the threshold of what is possible, yet never stepping beyond it. They are guardians of limits. If a star grows too ambitious, gravity reins it in. If a region of space becomes too dense, a horizon forms to preserve order. If energy tries to exceed its domain, time stretches and slows to keep it contained. If motion becomes too violent, drag appears, shedding excess into space. The universe always intervenes, gently but absolutely. These boundaries are not arbitrary. They arise from the fundamental shape of space-time, from geometry more than rule. They are the natural consequences of how the universe is built. Even the constants of nature, the speed of light, Planck's constant, the gravitational strength, are finely tuned values that allow stability. They are not easy numbers. They are the result of deep structure. The universe is not fragile. It is resilient by design. Tonight, as you breathe in the safety of ordered physical law, every boundary we've discussed supports your existence. The atoms in your body remain intact because quantum restrictions prevent infinite collapse. The Earth stays in orbit because motion and gravity form a perfect balance. Light reaches your eyes because it obeys a universal limit that ensures information arrives in proper time. You are not just living in a universe with limits. You are alive because they exist. Even death, even collapse, even black holes are not failures. They are transformations guided by principles that preserve meaning. Nothing ends without giving something back. Hawking radiation returns energy to the cosmos. Event horizons store the details of everything they consume. Entropy ensures memory is never erased, only translated. Balance keeps the future compatible with the past. This quiet law that power must respect structure carries across the entire universe. It prevents the cosmos from becoming a runaway engine. It ensures that every force, no matter how strong, is held in a gentle relationship with every other. There is humility in physics. Even the greatest giants bow to the same rules as the smallest particles. Perhaps that is the most beautiful truth of all. Everything belongs to a single system where no component can claim complete freedom at the expense of the rest. Shared limits are what allow shared existence. The universe does not restrain because it fears. It restrains because it cares. Because without structure, there would be no place for stars to shine, no foundation for planets to form, no environment for life to dream. As you settle into rest, as your own heartbeat finds its rhythm, remember that the same gentle boundaries guiding black holes guide you. You are shaped by cosmic laws that value continuity, balance, and possibility. In a universe full of unimaginable power, serenity comes from knowing that nothing can break the rules that sustain us. Nothing can overpower the geometry that gives meaning to existence. Nothing can escape the quiet embrace of the cosmos, not even a black hole, not even collapse, not even darkness. That is the law nothing can break, the law that keeps us here. As we now drift toward the close of this cosmic journey, held by the calm certainty of physics, a final question opens softly in the space between stars. If black holes must one day release all the energy they collect, if their horizons eventually fade into starlight, what remains? What legacy do these titans of gravity leave behind? Now, with a quiet breath, we turn to the outro. Even now, as the universe expands in silence, the greatest structures within it are slowly obeying these gentle laws. Black holes evaporate into light, singularities remain hidden behind horizons. Information scatters back into the cosmos like seeds waiting to bloom into new forms. Nothing is wasted, nothing is lost, everything transforms. The universe does not choose power without purpose. It chooses boundaries that make beauty possible. Every star, every planet, every pulse of life exists because the cosmos enforces balance at every scale, from the smallest quantum flicker to the deepest gravitational well. And you are part of that harmony. As you rest, the same quiet rules that protect black holes protect you. Gravity holds you close to Earth. Light moves with quiet precision to reach your eyes. Time guides each breath in a single direction, comforting in its certainty. There is peace in knowing that you are held by a universe that refuses chaos, a universe that values continuity, a universe that ensures the future can always trust the past. Tonight, may the calm logic behind existence bring you a soft sense of wonder. May the silent structure of spacetime cradle your thoughts gently. May the stars above remind you that even the dark has limits, and that even the most powerful forces are shaped by restraint. Thank you for sharing this quiet journey through the heart of cosmic law. Your presence here means more than you know. If this helped you, find a moment of peace, even a small one. I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps this calm corner of the universe continue its quiet work. For now, close your eyes. Breathe with the rhythm of the cosmos and rest in the assurance that everything, even the deepest shadows, is guided by balance. Good night.